Fantastic. Could I have your attention, please? I'd like to start the proceedings this morning. The first port of call is, as president of the EAG, one of my privileges to present and recognize excellence within the geochemistry community. And the first medal that I would like to present today is the most prestigious medal that the European Association of Geochemistry awards. That is recognizing an outstanding contribution advancing geochemistry over a career, and that is the URI Medal. And this year the URI Medal has been awarded to Ed Boyle, and I would like to invite Ed Boyle to come up to the podium and accept this medal. Please give him a round of applause. The second medal that it's my pleasure to present today is the Science Innovation Award Medal, this year named after Sam Epstein. We circulate the subject area. So the 2014 Epstein Medal, which recognizes important breakthroughs in geochemistry by mid-career scientists, is awarded this year to James Farquhar, and I'd like to invite James to come to the podium to accept this medal. James. And the next award I would like to present is the 2014 Hootermans Medal, which recognizes exceptional contributions to geochemistry by scientists under 35 years of age or within 6 years of their PhD. And I'd like to invite Li Ping to the podium to accept this award. Li Ping, please. And this year is the first time the European Association of Geochemistry has presented a new award, and this is the European Association of Geochemistry's Distinguished Service Award, recognizing outstanding service to the geochemical community, which exceeds the expectations of normal service. And it's my great pleasure to invite Juan Diego Rodriguez Blanco to the stage.
Thank you. Thank you very much.
Congratulations.
Thank you very much.
Well deserved.
Thank you. This is very appreciated.
Thank you all very much. I'd now like to pass the podium to Barbara Sherwood-Lawler.
We have one final award and distinction to present today from the Geochemical Society, the Distinguished Service Award. And in order to introduce and give the citation for this award, I'd like to invite our past president, Dr. Rick Carlson, to lead us through that part of the ceremony.
I have the honor of giving the Distinguished Service Award of the Geochemical Society. This award recognizes and documents outstanding service to the society or the geochemical community that greatly exceeds the normal expectations of service to the society. I'd like to give a few words about our winner, Carla Koretsky, this year. Carla's GS service includes being co-editor of the Geochemical News from 2001 to 2008, so a long tenure there, but importantly chairing the Goldschmidt Student Travel Grant Committee and serving as a principal investigator on the National Science Foundation grant that supported the student travel program from 2011 to 2013. In these latter roles, Carla and her committee dispersed a total of over $180,000 in travel grants that supported the participation of a total of 192 students at Goldschmidt conferences over those years. Managing the student support program involves a good deal of work, so the success of this program while under Carla's guidance is a clear display of the level of selfless service to the geochemical community for which she's being recognized with our appreciation today. So, Carla Koretsky.
Thank you very much. At this time, I'd like to invite one of the members of our local organizing committee for the California Goldschmidt, Dr. Charlie Albers, who will be introducing and leading us through the rest of the plenary.
Thank you, Barbara. Pleasure to be here. And on behalf of the local organizing committee, I want to welcome everyone to Sacramento. I'm going to introduce today's plenary speakers. Having done a little work myself in the realm of the environmental impacts of the gold rush, I want to take this opportunity to describe the little context of why it's important that we've got so much contamination of arsenic and mercury here in California. The slide on the left is a gold pan from one of our field areas where we started with a kilogram of sediment from one of these sluice tunnels draining a hydraulic mine, and ended up with 30 grams of mercury, so about 3 weight percent. Visible elemental mercury is still out there. And then on the right is a photograph from the Mojave Desert in an area where there's a lot of arsenic contamination from historic gold mine tailings. In this case, almost a weight percent of arsenic in the dust that these all-terrain vehicle riders are inhaling. Oops. Here we are very close to Sacramento, California's capital, and I want to just give a little historical perspective. The discovery of gold in 1848 was only a few kilometers to the east in the American River watershed. American River drains right here through Sacramento, and just a few days later, the United States purchased this large swath of land from the Mexican government for, at the time, $15 million was a lot of money, but I think if they'd known how much gold was out there, the price might have been a bit higher. The capital was built with revenues from the gold rush. There's a gold-plated sphere on the top of the Capitol, symbolic of the importance of gold in California. And money from the gold rush also helped the North win the Civil War in the U.S. in the 1860s. And I wanted to point out, if you get an opportunity to tour the Capitol, there's an excellent display on the ground floor of all the counties, all 56 counties of California. You can get a great idea of the diversity and the importance of mining and other economic activities and how diverse the state is. Another important historical fact was the Transcontinental Railroad, which was completed in 1869 in Utah. That railroad ended in California, again, because of the importance of California gold mining to the nation's economy. And but on the dark side of the gold rush, of course, there's the impact on Native Americans, many of whom did not survive that episode in history, and their native fisheries were largely decimated. The salmon runs are much reduced from what they were, absent in many areas because of dams and other contamination problems. Another important legacy you'll hear about from our speakers is mercury contamination in fish. This graphic on the left from the California Office of Environmental Health Hazard Assessment shows in the red symbols all the places that have advisories on on fish consumption because of mercury contamination. The blue symbols represent mercury mines in the Coast Ranges you'll be hearing a lot about from our speakers, and the brown symbols represent a small subset, just the largest of the gold mines in the Sierra Nevada and elsewhere, where mercury was used for amalgamation and led to mercury contamination. And so the state has issued this warning where these particular species, different species of bass, carp, and brown trout, are in the do not eat category in many water bodies for women of childbearing age and children, whereas lower trophic level fish such as rainbow trout are much lower in mercury and generally safe to eat. And I want to just point out previous work by Roger Ashley, my colleague at USGS, who showed this schematic cross-section in one of his publications showing how mercury and arsenic are both naturally occurring in hydrothermal systems. Mercury tends to concentrate in the superficial environment, the hot spring environment, and further down in these systems you tend to get the gold associated with antimony, and then arsenic in the mesozonal or mesothermal area as well as in the deeper zones. And the scale here in kilometers, 5, 10, 15 kilometers deep. The mother lode area being generally in this mesothermal area associated with green schist grade metamorphism. The mercury mines here occurring in the Coast Ranges in the red symbols, again, there's mercury contamination associated with those areas, but also the mercury which was transported to be used for gold extraction in the gold mining areas, particularly in the 19th century. And then finally, just want to point out again, the association of gold and arsenic can be seen in these samples. This one on the left, a specimen that shows native gold and a rather large clump of arsenopyrite. This one's from Nevada County, a few kilometers to the northeast of here, and in a SEM image showing both pyrite and arsenopyrite, which is the characteristic rhombohedral forms, again from Roger Ashley's samples. But the pyrite tends to include arsenic in it as well, as you will hear. Arsenian pyrite tends to be one of the most important hosts for arsenic in some parts of the Sierra Nevada. So with that context, I want to now introduce our speakers for this plenary session. Both Andrea Foster and Christopher Kim got their PhDs from Stanford University under the direction of Gordon Brown. They're experts in the field of X-ray synchrotron-based spectroscopy, so you'll be hearing a fair amount about the speciation of both arsenic and mercury. So I'd like you to welcome our speakers today, Andrea and Chris.
Great. Well, thanks, Charlie, for that introduction and overview, and welcome, everyone. I would like to thank, on behalf of Andrea and myself, the organizers of the Goldschmidt Conference for giving us this opportunity to deliver today's plenary. It's really quite an honor. And if I can get the next slide coming up right there. I do note, however, that our plenary was scheduled for Thursday towards the end of the week, and so it took that long for you to find out that you've been in the most mercury and arsenic-enriched part of our country. So I apologize for the kind of late notice there, but hopefully everybody's feeling okay today. In fact, California could very well have been referred to as the Mercury state because we have such large native deposits of mercury in the Coast Range, as Charlie mentioned. But of course, mercury is not a great element to be associated with. It's a neurotoxin, so that did not become our state motto, surprisingly. Neither does the arsenic state really make a really good kind of, it doesn't roll off the tongue quite as well. So California, the arsenic state, arsenic being a carcinogen, also not something we want to be associated with. So the founders of our state motto in their infinite wisdom decided that California, the Golden State, is a much better way to bring tourists to California, and that probably makes our tourism board a lot happier. But what I'm going to talk to you about to start out with is the deposition of mercury in California. This occurred as a result of a transition between a subduction zone environment to a transform zone environment about 29 million years ago. Of course, we're all very familiar with the San Andreas Fault Zone that's part of our transform zone environment we're in today. But this shift in tectonic environment caused a large heat anomaly to propagate from the southern part of the state up to the northern part of the state where we are right now. And this resulted in two forms of mercury deposition over that time frame. The first is referred to as silica carbonate mercury deposition. These are deposits that form at higher temperatures, deeper in the earth, and as logically the name indicates, associated with silica carbonate alteration rocks in the serpentinite bodies or surrounding the serpentinite bodies found in the California Coast Range. Two of the largest mercury deposits in California are named after the Almaden mine in Spain and the Andrea mine in Slovenia, correspondingly. The second level of mercury deposition, the more later stage, is referred to as the hot spring mercury deposits. These occur in contrast at shallower depths, lower temperatures, and the geochemistry of the waters that make up these deposits are slightly different. Specifically, they contain elevated levels of chloride, and that's an important fact I'll ask you to hold on to for the next few slides. So you are here in this red X right there among all the great mercury mines of the California Coast Range. And if we zoom in on this a little bit better, you can see symbols representing the different mercury mines. The crossed hammers represent silica carbonate deposits, of which the New Almaden mine is one, just south of San Francisco. The yellow squares represent hot spring mercury deposits. The Sulfur Bank mine is one of the more well-known ones. It's a Superfund site just on the edge of Clear Lake, north of Napa Valley. And the USGS has put together a really nice fact sheet that combines, or that shows all of the interrelationships between mercury mining and gold mining throughout the state. So let me just show these kind of one piece at a time. Here's a schematic showing the basic setup of a mercury mine. We have mercury ores and waste rock over here to the left of the image, and we have the mine waste over here to the right. When the ore is crushed and roasted at elevated temperatures, several hundred degrees centigrade, that has the effect of volatilizing the mercury as elemental mercury, where it can then be cooled, condensed, and collected. But the residual material is still relatively high in mercury, primarily as mercury sulfide. So we've got the ore, the waste rock, the mine waste, and current depositions in hot springs that contribute to a high potential for mercury contamination, both at the mine sites themselves and in the surrounding areas. Here's a chunk of what that mercury ore looks like on the left. You can see the cinnabar pretty visibly. It's a bright red mineral. There's also a little amount of native elemental mercury present. And on the right is kind of the end member of that whole process, the calcines, or the roasted material, which you can see is very fine-grained, poorly consolidated, or rather unconsolidated, and very easily eroded and transported downstream and downslope. As Charlie mentioned, we are, I'm going to say experts, I guess. Well, we've spent a lot of time doing X-ray spectroscopy, and so this is one of hopefully just a handful of X-ray spectra we'll make you look at today. But it's important to show that we can actually use this method to determine the speciation of mercury and arsenic in natural heterogeneous materials. The black line here represents a mercury EXAFS spectrum of a Turkey-run mine calcine, and above that, or right on top of it, is a red line representing the best fit we can make to that data. That's conducted through a process called linear combination fitting, whereby using a kind of forensic fingerprinting technique, we match that unknown spectrum with a host of spectra previously collected of well-characterized mercury phases. And you can see those two below, cinnabar and metacinnabar, which contribute roughly to 58% and 42% respectively. So that gives us both the identification and the quantification of those phases in that sample. If we apply the same method to samples from both the silica carbonate deposits and the mercury, the hot spring mercury deposits, we can see some clear differences in the speciation. Although both contain large amounts of cinnabar and metacinnabar, we also see montroidite and shooteite in the silica carbonate deposits. That's a mercury oxide and mercury oxysulfate phase. And in the hot spring deposits, we see a host of mercury chloride phases, which is consistent with the elevated chloride levels in the hot spring deposits I mentioned earlier. So this is important for two reasons. One, it validates that we can use EXAFS spectroscopy to actually differentiate these two depositional environments. And two, it reminds us that mercury speciation is quite different. And that has importance from an environmental perspective, since mercury's phases vary by tens of orders of magnitude in solubility, with the chloride species in particular being very soluble. Some more recent work by Adam Jew et al. Has added to our ability to do speciation analyses by showing that if you cool samples down to liquid nitrogen temperatures very slowly, we can actually crystallize the elemental mercury into a solid crystalline form, which makes it much more easy to identify, as shown by the black spectrum, compared to the room temperature spectrum of elemental mercury. And here's a nice historical image showing those condenser columns. As I mentioned before, mercury is volatilized, cools, condenses, and is collected and stored in these 76-pound mercury flasks. And as was mentioned earlier, the reason for all this mercury mining was because of the discovery of gold in California in the mid-1800s. So here's our stereotypical miner, we'll say. And the discovery of gold, rather, spurred the large production of elemental mercury in the Coast Range, and then transported it from the Coast Range out to these gold deposits for use in gold recovery. This was done because mercury, among many other unique properties of it, is very excellent at amalgamating other metals. And so whenever any gold would make contact with mercury, it would be amalgamated and could be recovered later. So if we look at this fact sheet again, I'll just show the three different methods of gold mining that took place over time that were a function of the geology of the gold deposit, improvements in technology and mining technology, as well as various regulatory policy efforts. But the main thing that connects all of these is that they all utilized elemental mercury to great extent. Here's a photo of hydraulic mining, a fairly destructive process whereby high-powered water jets were used to wash placer gold ores downstream into these sluices in which were charged little pools of elemental mercury. So any fine-grained gold that washed over the mercury would connect with it and amalgamate and could later be separated and recovered. Miners got very good at separating the coarse material, shown in the sluice box here, with a very fine-grained material called the undercurrent, and that aided and enhanced gold recovery, but it was also fairly environmentally damaging, as you can imagine. The introduction of stamp mills, which were basically these 2-ton steel plates that would crush material down to 100 microns in size or so, further enhanced recovery by increasing the surface area and the reactivity of these gold ores. And here's a nice image showing some of these, a series of these stamp mills, and then these beds, which were basically copper sheets lined with a very thin film of elemental mercury. As the stamp milled, very fine-grained material passed over it, again, the gold would amalgamate with the mercury. So this process of mercury and gold mining released, as you might imagine, large amounts of mercury into the environment as well as the atmosphere. Historically, 100 million kilograms of mercury were produced in the California Coast Range, with an additional 33 million kilograms lost to the atmosphere through the roasting process. Of those 100 million kilograms, actually 88% of it was exported globally for other purposes, with 12 million kilograms used in California gold mining, and it's been estimated about 5 million of those kilograms have been lost in the process. And when I put this together, I realized 5 million kilograms is the smallest box here, so it looks very unimpressive. So for comparison, I'll show you the amount, now it looks a lot bigger, right? But this is the amount of mercury that's released into the atmosphere annually due to global emissions from coal burning. So you can see it's about 10 orders of magnitude, or an order of magnitude larger than that. And as Charlie mentioned, this lost mercury largely persists as elemental mercury. You can still pan it out from these sluice areas. But there's some evidence now that this elemental mercury may be transforming very slowly over time. This is a very noisy EXAFS spectrum, I'll acknowledge, because it's a very low concentration. But this is work by Aaron Slowey et al., who showed that a sample of these gold mine tailings actually now shows evidence from the Fourier transform on the right that mercury is now associated with sulfur in both the distances and the coordination numbers consistent with that of cinnabar. So we may actually be seeing very slow reoxidation of this elemental mercury and then conversion back to cinnabar. So we've caused quite a mess over time with gold and mercury now in the Coast Ranges as well as in the Sierra Nevadas, and this is evident by the number of consumption advisories for fish consumption, both in the areas where mercury mining took place as well as the areas where gold mining took place. And most people are aware of this, and it's fairly well known in the public, that mercury can build up through the food chain. Before doing so, it needs to be converted typically from inorganic forms into an organic form. This is the most common organic form that we're worried about is methylmercury, which a number of people probably in this room have spent a lot of time studying. It's a microbially mediated process, typically facilitated by sulfate-reducing bacteria. But it's this kind of bioaccumulation and biomagnification process, which is quite critical. Bioaccumulation means an upconcentration from surrounding media, such as water, into the lower part of the food web, which in this case are algae. So that's the bioaccumulation process. And then the buildup in the food web to zooplankton, lower order fish, and then higher order predator fish is the term called biomagnification. And so the result of this is an increase by sometimes 7 orders of magnitude from the water into these higher order fish. So you might be looking at parts per trillion levels in the water and parts per million levels in the fish. And this methylmercury form was identified conclusively by looking at the Zane's spectra of commercial fish just purchased at a store. And you can see that this fits very well with, among 5 different mercury compounds, it fits best with methylmercury bound to a sulfur group, specifically cysteine in this example. And just an interesting micro XRF image collected also at a synchrotron shows interestingly, that mercury not only concentrates in target organs, but in this cross-section of a zebrafish head is concentrating very intensely in the eyeballs of that zebrafish. And so there's perhaps some implication there that the blurred vision or the vision impairment that is often associated in humans with mercury contamination may not be actually a neurotoxic effect, but may actually be an effect of accumulation of mercury in the eyeballs. So if only mercury was the problem in these areas, then we'd still have plenty to work on for the next several decades. But in fact, as was mentioned before, arsenic is also a problem, was discovered a little later on in the history of this gold mining process. And so with that, I'm going to turn things over to my co-presenter, Andrea, to tell us about arsenic and gold mines.
Thanks, Chris. Chris will be back. Don't clap yet. He'll be back. So if we could have the slides going. So I'm showing you a map here of the California. It's slightly rotated and a little bit old, but showing the counties. I've colored Sacramento County in gray so you can get a sense of where you are right now. And hopefully you can see back there the black dots. They are the gold mining districts. Each district would contain more than one mine, usually, of California. And I hope you can see that there's a strong clustering of those districts right around where we are today. Furthermore, there's a kind of north-south trend to those cluster of points. I'm pointing over here. This area contains most of the lode type deposits that we have here in California. They're on the western side of the Sierra Nevada mountain range. We typically call it the foothills region. This area, there's a tight structural control on the location of these deposits, as Charlie showed us earlier in that geologic map. The ore-forming fluids came up along regional scale fractures in the crust, and that's why they're all so located along that band. We can roughly delineate northern and southern components of the system, but for you trivia buffs, the true mother lode districts are located in the southern portion along one specific fault, the Maloney's Fault Zone. So pyrite and arsenopyrite are the main primary arsenic-bearing phases, as Charlie mentioned, and the type and quantity of those two really control the initial arsenic concentrations we have in the ore. The table on top is showing that arsenopyrite contains about 46% weight arsenic and is concentrated in the northern lobe that I just showed you. Arsenian or arsenic-bearing pyrites around here contain about 2% weight. They can contain up to about 6 theoretical limits, and they are found in both the northern and southern lobes. So the bottom plot is a log-log plot of arsenic and gold, illustrating that although gold grades are roughly equivalent, ranging in values, of course, but southern and northern deposits have roughly similar grades. Arsenic concentrations are much higher in the northern deposits. I've shaded that region in the tan color. So at the extremes, about a 3 to 4 order of magnitude concentration of arsenic. People have observed for a long time in electron micrograph data such as this, that arsenic distributions in pyrite are heterogeneous. So we're looking at some data from Kay Savage's work, another colleague from Stanford, where the bright colors are high concentrations of arsenic, 4% weight. The average concentration, again, is about 2. But you can see that the distribution is quite heterogeneous. People have often wondered, what does that mean for the local structure of arsenic in pyrite? That was one of the first subjects that Kay attacked in her studies, and she showed that arsenic indeed substitutes for sulfur in our pyrites around here. She's showing the fit to the data in the dotted line using a structural model of arsenic, again, substituting for sulfur, but one in which there are about 30% arsenic neighbors. So there is a degree of clustering of arsenic in the pyrite that may affect its reactivity. That's some of Kay's later work. And she's comparing on the bottom there to the spectrum of arsenopyrite just to make that point a little bit stronger. So the processing that went on at the lode gold or hard rock deposits served to redistribute these sulfides. The original ore, as Charlie showed us, was free gold in association with quartz. Unlike the picture that we saw, though, sulfides were usually low abundant in the actual ore. They were rather higher in the waste rock that accompanied the ore that was usually left on site or backfilled into the underground workings. Later on in gold mining, the sulfides themselves were exploited for the lower concentrations of gold that they contain, using froth flotation mechanisms to separate the sulfides from the other matrix. Those methods were selective, or more efficient rather, for pyrite, leading to a relative increase in arsenopyrite abundance in the residual milled tailings. As Chris showed us with the stamp mill, a lot of grinding of this material went on, which increases reactive surface area. Once cyanidation came online and replaced mercury amalgamation, the materials had to be ground up still further So you actually have tailings that have almost a flour-like consistency, making them very reactive in the environment. Luckily for us, though, the mine waters draining these piles and also mine adits tend to be near neutral because of the abundance of carbonate phases and other buffering minerals. However, locally, very locally, where sulfide concentrates were left on site, you can have acid mine situations. I'm not going to talk a whole lot about arsenic in water, but I did want to draw a couple of contrasts to what Chris just told you about mercury. Unlike the situation with mercury, the organo-arsenic species, of which there are many, and a strong biotic component, they don't tend to be very toxic or necessarily biomagnified, though they can accumulate. A lot of interesting spectroscopy has been done that I'm not going to have time to show you. Rather, it's these inorganic forms here, the oxoanions of arsenic, that are known to cause problems, at least to humans. There's not been clear evidence, though, that here in California we are having severe impacts to biota because of high arsenic concentrations from mining. So we've seen that weathering of all those solid products I just showed you produces additional arsenic-rich solids. Weathering of pyrite, low arsenic pyrite, produces iron oxides that tend to have less than 1% arsenic, but weathering of Arsenian pyrite can produce phases such as these sulfates, jarosite, and copiapite that can have up to 1 weight percent. And furthermore, the iron oxyhydroxides produced from Arsenian pyrite can be yet still more concentrated. We've measured arsenic in those phases up to about 6 weight percent. Weathering of arsenopyrite generates phases with even higher residual arsenic concentrations. We've seen up to 20 weight percent in the residual iron oxides that are produced from arsenopyrite weathering. And we also see a suite of arsenate minerals forming. The middle phase, their hydrospheric arsenate, is a material that's still a subject of a lot of study right now. The structure is not really well known, mostly because it occurs as a poorly crystalline material. One idea is that it's a nanophase mixture of ferrihydrite and the mineral scorodite, which I'm showing below. Another important class of secondary arsenates are the calcium iron arsenates. I'm illustrating arsenosiderite here. So all three of those phases have arsenic in roughly 20 to 30 weight percent. We've also noticed that biogenic oxyhydroxides, iron oxyhydroxides, are accumulating arsenic at these mine sites. We studied iron oxidizing communities dominated by the filamentous sheath-forming bacterium Leptothrix at the Lava Cap mine. And this is a box plot of arsenic in parts per million, milligrams per kilogram, illustrating some of the dry weight arsenic compositions, concentrations that we got. I just want to draw your attention to that one box that's much higher than the rest. That's material collected from this small tailings, small pond in tailings. And the initial dissolved arsenic concentrations were quite high, so the resulting solid phase arsenic concentrations, median values of about 17,000 parts per million, about 1.7 weight percent. Significant elevations relative to the tailings, which I'm showing as that yellow bar down there, about 500 to 1,000 milligrams per kilogram. So one application of synchrotron radiation to arsenic studies that's been really useful is characterizing these X-ray amorphous or difficult to study materials such as these oxyhydroxides of biogenic materials. Studying this actual material that I'm showing in the picture, using the linear combination fitting that Chris mentioned earlier, we see a good match to a model compound of arsenic 5 sorbed to iron oxyhydroxide and a small component of arsenite, the reduced form of arsenic. We can also do the type of theoretical fits that I mentioned for Kay Savage's work on pyrite. When we do that type of fitting, we get more information, detailed information about the geometry of the sorbed complexes, which I'm showing you there. I'm not going to go into all the details, but the point is that you get two complementary types of information, and this information is very valuable to understand the stability of these complexes. Another important application of synchrotron radiation has been to examining the reaction products of weathering at the micron scale. And a really beautiful example of that shown here, coming out of Heather Jabeson's research group up in Queen's University in Canada. They were looking at gold mine tailings in Nova Scotia, arsenopyrite rich, that's shown by the dark gray particles here that are being weathered to those lighter yellow and orange phases. They've taken 3 micro XRD patterns in a transect across those, and they're finding scorodite, quite well crystalline there on top, and the bottom 2 are much less crystalline. You can see by the broad XRD patterns. On the bottom, I'd like to draw your attention to the phase thuleite. It's a ferric arsenite mineral, so that's a mixed valent, indicative of a mixed redox situation. We haven't seen thuleite here in California, but it may be because of climatic differences. We enjoy this Mediterranean climate, rather more oxidizing situation than the heavier rain and colder conditions up in Nova Scotia. So some studies of similar deposits as a function of climate could be an interesting area for future research. Another application of synchrotron radiation has been to quantify changes as a function of some kind of perturbation. And to examine that, let's go back to the lava cap mine, which is on the EPA's national priority list, or we call Superfund, of the most contaminated sites in the country. And I'll tell you a little bit about what happened there. The middle panel shows a modified topographic map of the site, and there was a dam located where it says failed tailings dam. It did burst after a flooding due to a heavy storm event, one of the type of events that's predicted to occur more and more with climate change. The image, the picture, shows you the scarp that was left after the dam burst, and large volume of tailings migrated from the mine site down Little Clipper Creek and into Lost Lake, which I've blown up in that image. I've shaded in gray a sort of tailings delta region that was left by the deposition of those tailings, but the tailings also made it all the way into the lake, raised the lake level temporarily, and then the water subsided again, leaving a kind of bathtub ring around the lake. Here you can see a little girl playing in those newly deposited tailings. They're about 1,000, 1,500 milligrams per kilogram, as I mentioned earlier. The lake is shown there in a picture. It's a private lake completely surrounded by houses, and the people that lived there enjoyed recreational activities, including swimming and boating, fishing, until knowledge of that they were actually enjoying a tailings reservoir lake sort of was remembered. So we were interested in seeing what was going to happen to these exposed tailings. And we used first principal components analysis to investigate the whole set of EXAFS spectra that we collected from the site. So in this type of analysis, each point that you're looking at is an individual EXAFS spectrum, and the proximity of the points is directly related to the similarity of the spectra. So identical spectra would have exactly overlaying points. And what should pop out, hopefully, to you is that the red dots, which were tailings that were submerged in the lake that had never been exposed or minimally exposed to oxidation over about 70 years, is very similar to the black dot, which is a sample of arsenopyrite-rich ore that we collected from the site. Pyrite-rich ore, represented by my one sample in the far corner there, is quite a bit different. And further, finally, exposed tailings that were in this bathtub ring are themselves separated by this analysis. This type of analysis is model independent. We do no fitting yet. So it's interesting to compare that with actual fits, linear combination fits, as Chris and I have been talking about. The main difference then between the submerged and exposed tailings is the loss of arsenopyrite, roughly about 30%, and the gain of arsenic, again, sorbed on hydrospheric oxide, which turns out to be nature's sponge for arsenic and everything else. So we know that ingestion of water is a serious pathway for arsenic exposure because of the, unfortunately, common occurrence of naturally occurring arsenic in groundwater and the problems that it's created around the world. Right now, a real active area of research is looking at the hazards related to particle ingestion and inhalation, the solid phases. And that's what we'll be focusing on now. So this table attempts to synthesize information from several studies and also just common geochemical wisdom about the solubility of all the phases that we've described and the pH and other chemical conditions of fluids in our bodies. So going from the top, if we think about the ingestion pathway, we have the very acidic gastric fluid, the near-neutral intestinal fluid, and we also have a column I've called substrate reducible. That's in recognition of the new data showing that the microbial community in our gut also plays a strong role, particularly in the reduction of any redox-sensitive substrates and potential release of arsenic. Of course, there are bacteria that also can reduce arsenate themselves, but I'm not considering them in this table. In the inhalation pathway, we have the bulk lung fluid, which is again near neutral, and we have the very long word that didn't fit, phagolysosomal fluid. This is inside the alveolar macrophages, and it's slightly acidic. There's also more chemistry in there. So based on all that knowledge, let's kind of quickly go through this table. The sulfide minerals, arsenopyrite and pyrite specifically, are predicted to not have a real strong dissolution factor under these conditions. I've put a check mark by the phagolysosomal because there's more chemistry going on there, including, I believe, peroxidases, oxidizing species. The iron arsenates and sulfates like scorodite and jarosite would be stable under gastric fluid conditions, but would be predicted to dissolve and release arsenic under the more near neutral conditions, and are also reducible. They have ferric iron. However, it's known that they dissolve incongruently. They form hydrous ferric oxides, again, above pH about 4.5. So it's likely that they'll release arsenic and then take it back up again. Whether that really happens has not been definitively established, but for that reason, we estimate that they may have low bioaccessibility or they may release less arsenic. Arsenio-siderite, this calcium iron arsenate, would be predicted to dissolve under acidic conditions and is also reducible. And then the bottom two rows, I try to represent sorbed arsenic species. Arsenic 3 in the red and arsenic 5 there in black. When sorbed onto hydrous aluminum oxides, such as a gibbsite or clay minerals, that arsenic is quite labile, laboratory studies have shown. So we would predict a lot of that arsenic would come off under these bodily fluid conditions. The situation is a little bit different for arsenic sorbed onto ferrihydrite. Arsenic 5 has a really strong affinity for ferrihydrite. It's going to stick under a lot of conditions. Arsenite, somewhat less so. So we've tried to illustrate that, but it is substrate reducible. So overall, we conclude that it's these three bottom rows, the sorbed arsenic and arsenio-siderite, that may be the most bioaccessible, have the most bioaccessible forms of arsenic. But now you see the importance of speciation here and why we care about it so much for exposure route. So one of the big challenges for the California foothills region is what to do with all these mined areas, these land masses that we'd like to do something with. And one notorious example of how redeveloping these areas can go wrong was at Mesa de Oro. For those of you who are up on your Spanish, know that Mesa refers to a tall, flat-topped hill. In this case, the hill was made out of mine tailings from the Central Eureka mine right across the street there. When residents found out that their homes were built on mine wastes, they were kind of upset, and the news made national headlines. This is a kind of ugly newspaper clipping from the time, and there were a lot of lawsuits. Some people argued that residents shouldn't get so upset because the original form of arsenic in the tailings was arsenopyrite. I mentioned how some tailings can be arsenopyrite rich. So we decided to go on and try to investigate that a little bit, and we used X-ray absorption near-edge spectroscopy of arsenic to do that. So what you're looking at here is a spectrum of arsenopyrite in black and a spectrum of this arsenate adsorbed onto iron oxyhydroxide in blue. You can see a very dramatic offset of those spectra in energy. That's a very sensitive indicator of oxidation state for us. So we went and sampled 4 soils from the mesa, surface soils, and collected their spectra. And I'm just showing in this vertical bar where their positions of their peaks were. And you can see that it's coinciding with arsenate, showing that indeed the arsenopyrite, the sulfide-bearing arsenic that was present, is now gone by our analyses. And indeed, some of those soils had relatively high bioavailability when subjected to testing. So right now we're working with in a multi-institutional study at the Empire Mine State Park, and I hope to talk to some of you who will join us on the field trip to that site on Saturday. The study is funded by Environmental Protection Agency and run by the Department of Toxic Substances Control. And our goal is to get a better predictive and process-based understanding of the relation between speciation and bioavailability as measured for us in juvenile swine, and bioaccessibility, that's the lab equivalent measurement. I won't talk too much about the data because we're going to go back. There'll be more talks, posters this evening about that in session 20G posters, and also tomorrow we'll be talking about that in the oral session. But I will show just a little bit of data to make the point that the species that we are observing are similar to those that have been found in other deposits around the world. And to show that, we're looking at some microprobe data, and so things are cast in terms of oxides here, from the Quetzal River mine up in the Yukon, Canada. This is my colleague Dogan Pektunk's work. He's showing that we have the complete range of arsenic concentrations and iron-arsenic ratios. These ratios can be quite distinctive for various phases. You see that he's got quite a few phases up in the arsenate mineral zone, but he also has quite a few down in the adsorbed region. In the middle is a region where we're not really always sure about what the speciation is, again, because of this hydrospheric arsenate I mentioned, which has a questionable coordination. If I switch now and show you the same plot for Empire Mine samples, these data were collected by Tamsin Burlack, a master's student right down the street at Sacramento State University. You can see that we have quite a few more points down in the absorption regime, and fewer up in the ferric arsenate minerals. The Quetzal River mine tailings are much higher concentration of arsenic, almost 6 weight% relative to our materials, which range but max out at about 1.2 weight% total arsenic. So that's one reason. Looking at a similar type of plot for calcium versus arsenic now, you can see that in the Quetzal River mine, we have a cluster of points for this, again, calcium, iron, arsenate, but also an interesting trend that Dogan talked a lot about down here in the low zone. Comparing that to the Empire mine again, you can see that that low trend is actually pretty much gone, and neither do we have a lot of arsenio-siderite here at the Empire mine, but we do have this interesting cluster of points with the label G1 that don't match any known calcium arsenate compositions. So that is an area that we plan to study further. So with that, I'm going to turn it back over to Chris, and he's going to pick up the story in the Mojave.
Great. Thanks, Andrea. Go ahead to the next slide here. So we're going to take you out of the Sierra Nevada right now, where we spent quite a bit of time and hopefully learned quite a bit, down to Southern California, where a number of gold mines were also discovered but exploited considerably later during the gold rush in about 1890s or so. As a result, mercury amalgamation was not used there. Andrea mentioned that cyanide leaching was instead used. So there's no mercury contamination or very little mercury contamination in these regions, and the cyanide itself is degraded over time. Unfortunately, there's still quite a lot of arsenic in these regions, and that's what we've been studying quite a bit. Chapman University is located in Orange County, California, just east of and south of Los Angeles. So I'll tell you about some of these mines that we've been spending some time at. Here's an image of the Descarga tailings pile in Randsburg, California, part of the Randsburg Historic Mining District, just in the western Mojave Desert. You can see 800,000 tons of very fine-grained, gold-depleted but arsenic-enriched tailings there, with the town of Randsburg off to the right. And even though there have been some efforts to try and retain that material, there's still quite a lot of erosion that's happening downslope, as well as wind that's been blowing this material up and over the hills and towards the town of Randsburg. In addition to not using mercury amalgamation in Southern California for gold, some other differences with these mines are that, one, we're in a very low humidity, low precipitation, low vegetation, and very high wind speed environment. And that means that mine tailings get to be blown around quite a bit by airborne transport, such as through windstorms. The rare rain events that do occur through kind of these very intense rainstorm events, and you can see some of this material being brought, fortunately at least, through an engineered channel off of this tailings pile. And of course, as has been shown a few times before, human activity also plays a role in arsenic exposure. So a very popular pastime in Southern California, a big family pastime actually, is to ride ATVs all around. And because it's a family pastime, that usually means one of the parents, the father or mother, is going first, and all the kids are coming behind, sucking up big volumes of arsenic-enriched dust. So that's not so good news. And it also emphasizes that particle size and particle size distribution plays an important role, not only in the mobility of material, but also in the potential health impacts of that material. So this is an image from Jeff Plumley's chapter on medical geochemistry that illustrates this very well. It shows that particles in the 5 to 10 micron size range tend to be captured by the nasal cavity and the mucous membranes and don't make their way very deep into the respiratory system. Whereas particles that are maybe 1 to 2 microns in size can actually make their way down into the alveoli, where they can be captured and engulfed by these alveolar macrophages that Andrea mentioned earlier, dissolved, and then that arsenic can then be mobilized into the human body. We've done a lot of work looking at size and size distribution, as well as have many others, and they've found fairly universally that trace metal and metalloid concentration tends to vary inversely with particle size. So when we do mechanical separation through sieving of bulk mine tailings, we can see that in the finest grain particle sizes, this is one that's around, I guess, 20 to 32 microns in size, has a concentration of arsenic over 8,000 ppm, which is around 3 times greater than that of the bulk arsenic concentration prior to sieving. So this is kind of a bad news scenario where fine particles travel farther, get deeper into the lung, and contain higher levels of arsenic. But it also, again, emphasizes that speciation is an important thing for us to try and get a handle on. We've been doing, as was mentioned, a lot of work at the Empire Mine. These are a series of simulated gastric fluid in vitro extractions of arsenic-bearing mine tailings that have been, again, size separated. And there's a lot of different trends going on here. I'll direct you to a poster later on today to talk about them more. But one of the key things to note is that we have a general relationship between concentration and therefore particle size as it relates to bioaccessibility of arsenic, but that we also see quite a lot of variation at given arsenic concentration values. And this means that other factors such as arsenic speciation, particle size, surface area, and so forth must also play a key role. So we're actively investigating that. We also see this with lung fluid extractions, or more specifically, phagolysosomal simulant fluid extractions. So we're trying to simulate the interior of those macrophages. And when we look at just the 20 micron and below size fraction, we can see across a number of different mine sites a similar trend in arsenic concentration or particle size, predicting arsenic bioaccessibility, but we also still see regions where we have some variability that we haven't yet explained yet. Synchrotron-based X-ray methods, as we've hammered home probably quite a lot of times, can help with understanding arsenic speciation. Here's an X-ray fluorescence map showing some of these respirable particles. Iron's in blue, arsenic is in red. And for those of you who remember your color wheels, purple means that the iron and arsenic are co-located. And if you have very good eyesight, you can probably note that there's different hues of purple in this image. That means that arsenic and iron are present in different proportions. And when we actually take this plot and express it as a scatter plot, you can see that those, the pixels of this map kind of congregate into different populations or fingers, as we call them. And those probably represent different arsenic to iron stoichiometries in different phases. So if we take this micro-XRF map, or the scatter plot specifically, and compare that to the bulk EXAFS spectroscopy we've done on these same samples, we found 3 discrete phases, which hopefully not coincidentally match these arsenic to iron ratios. First, we have a sodium arsenate phase that was identified, which probably honestly is a proxy for a range of arsenic or iron-free arsenate species, where arsenic is much greater than iron. We've also identified arsenosiderite, a calcium iron arsenate that Andrea mentioned earlier, which has a 1-to-1 arsenic to iron ratio. And then the third phase is that relatively ubiquitous form of sorbed arsenic onto ferrihydrite, which has a very low arsenic to iron ratio. So we see a good correlation between the microscale analyses and the bulk analyses in this regard. We've also looked quite a bit at arsenic speciation in mine tailings, and you can see the axes here are the percentage of sodium arsenate, or this, again, iron-free arsenate family, versus arsenic that's absorbed to iron oxyhydroxides. And there's a negative relationship here, which kind of continues as we look at the downstream sediments, where we only see absorbed arsenic. So what this suggests to us is that arsenic speciation is actually changing with weathering, where we see dissolution of the more crystalline phases and then reabsorption of that arsenic onto the fine-grained iron hydroxides. Some of Andrea's work has also shown that this arsenic has a really key impact on some of the biota in this region. There's actually a desert tortoise preserve just adjacent to some of these mines, and by looking at some of the shell cross-sections of these desert tortoises, she's observed that there is arsenic metabolized in the shell as well as individual little particulates. And what's interesting also to note is that there are different oxidation states present throughout the shell. So with that, I'm going to turn things over one more time to Andrea to share some conclusions.
Thanks, Chris. So what we've seen, hopefully today, I tried to show you, the dynamic transformation of both arsenic and mercury in these mining environments. Starting with mercury, we begin with mercury in sulfide minerals or in these mercury chlorides that Chris described. And the processing, the roasting and calcining of the ore produces elemental mercury and oxychlorides and sulfides that are mercury in the 2+ state. Further dispersion of those materials throughout the environment produces, Chris showed us, actually there's some evidence that elemental mercury is retransformed into mercury sulfides, but what's key to understand is the small amount of mercury 0 that becomes ionic mercury, mercury 2. That is the material, that's a necessary precursor to the formation of methyl mercury, and it's the formation of that methyl mercury that's the real problem with mercury in general. Also, mercury that's sorbed to iron and aluminum oxyhydroxides is labile, has the potential to desorb, and again, participate in methylation and demethylation reactions. All of this happens through a process of chemical and physical weathering. Similarly, for arsenic, starting with the sulfide minerals arsenopyrite and pyrite, we essentially oxidize them in tailings and these sulfide concentrates, and forming a range of arsenates, sulfates, and sorbed species that I've showed you have range of solubilities and therefore potential bioavailability. Again, dispersion of those materials in pit lakes, retention ponds that we saw, Lost Lake, soils and stream sediments, underground workings, and even into groundwater can create problems. And always you have this redox transformation between arsenic 3 and arsenic 5 going on with arsenic. So, and I hope we were also able to make the point that synchrotron X-ray methods have really produced some valuable science in this area. First of all, we can see the oxidation state of phases such as arsenic. It's very dramatic, and even that information can be very useful. But on top of that, being able to identify the species and also determine their relative abundance can give us some, at both bulk and micron scale, can give us some really key information that's needed to understand the processes behind formation of these and to estimate the risks or hazards associated with different materials. Again, that's highlighted here in terms of the spatial distribution. I showed you those diffraction patterns of chemical weathering at the micron scale, very important for process level understanding. And finally, all that kind of information can help us better inform and predict these macroscopic laboratory tests that we do to try to understand the hazards to human health represented by these materials. So oops, too fast. With that, I'd like to acknowledge our funding sources and collaborators. Of course, for both Chris and I, there are many of them, but we'd like to single out Jim Raituba and Roger Ashley, both from the USGS, that have been really instrumental in helping us both in various aspects of our research. And of course, last but not least, our advisor, Gordon Brown, Jr., who got us started in the world of mercury and arsenic research. So with that, we'd be happy to take your questions. Thank you.
The discussion of gastric fluids got people thinking about lunchtime.
My question is, what do you think the ultimate health hazard will be to citizens of California, visitors like these, when they go out and sample cuisine, like fish, air samples, dust samples, and so forth, just through the normal process of living here?
So the question had to do with what are the health effects, perhaps to Californians, I guess, statewide. And you know, there's a lot of variability there, honestly. It depends a lot on the exposure pathway, whether you're looking at chronic, long-term effects or acute effects. And we've been doing some work in trying to assess that through in vitro studies. Also, in vivo studies are quite important. We found actually, at least down in Southern California, where I've done most recent work, the form of arsenic there is actually relatively insoluble. And when we actually multiply this by various risk factors, we found that we're generally consistently under the simulated, the gastric levels that would result in toxicity, but through the inhalation pathway that's much less well understood, and it's possible that inhalation, which is something we can do less about, is perhaps an exposure route that might be much more important. We're just starting to get into that now. With ingestion, there are easy ways to reduce your exposure through washing your hands, your food a little better by wet mopping your house and so forth. But with ingestion, or with inhalation rather, there's not much you can do to breathe less. So that's part of the problem.
Would you buy a house at Mesa de Oro, Andrea?
No, I wouldn't buy a house in Mesa de Oro. And I would add a little bit to Chris's response that the commercial fish that we eat, not only derived from California, but from around the world, was used in the study that Chris showed you of the mercury in fish. So that impacts all of us. In addition, there's been some work on arsenic in seaweed collected right off the coast of California. Again, the forms are these organoarsenic forms that aren't thought necessarily to be that toxic. But in the paper, our colleague Graham George did that work, and he discusses how some of the forms they're observing with X-ray absorption spectroscopy may indeed be hazardous, more hazardous than the organoarsenic forms. So we do have to watch what we eat.
At one of the earlier sessions, they were pointing out that they're now starting to worry about antimony as well. Have you looked at to see if they're, because I noticed one of the gold deposits also has antimony. Have you started to look at antimony or just even to see if it's there?
I have not, and you're right, very astute observation. I'm not familiar with the distribution of antimony deposits. Those were right in the middle between the mercury deposits and the arsenic-rich gold deposits. Charlie would probably be the best one. Chris, do you have anything to add there?
I would also punt that one to Charlie.
Let's talk to Charlie about that one later.
My question is how finely, you mentioned that in a lot of these tailings they're very fine particles. I'm wondering how small they are and how wide they might be distributed. So could they be affecting people outside of California?
Right, oh, thanks for that question. The stamp milling process tended to produce material from about 100 to 250 microns in size. So that gets deposited fairly readily, at least once it's airborne in the near region. The very fine-grained material, less than 20 microns, 10, 5 microns, is, of course, much higher in arsenic, so it's of greater concern, and it can be distributed much more widely. So we have done a few studies looking at airborne transport in these regions. We haven't really gone that far out yet to determine whether those signatures really extend across state boundaries. But they're certainly spread, in the several kilometers range away from these sources. But as far as kind of larger global cycles, I don't think that's been identified as a particularly big problem, at least not yet.
Do you have any sense of if there's potential health impacts from the ATV, like the family ATVing? Would the following the trailing ATVs potentially be exposed to enough arsenic or other metals to be of concern, or metalloids?
So the question was whether there are any documented health effects from ATV usage other than rolling those things over onto yourself. There are none that I'm aware of. It's kind of a pretty politically charged issue, as you might imagine, in that area, because many of those paths are really popular to ride on. And we've submitted an NSF proposal to actually study specifically the composition of those dusts as they're being blown off of these ATVs. So hopefully that will give us a little bit of insight. Again, it depends on your frequency of that activity and the distance you're taking from the ATV in front of you, as well as what trails you're using. So we're really interested in actually looking at that in more detail.
Of course, the key health consideration is dose, and part of that is how quickly the body can get rid of this stuff. Is there a knowledge about just the sort of a timescale of cleansing that the body is able to perform for either arsenic or mercury?
Sorry, I couldn't understand the question very well.
Just what is the rate at which the body gets rid of these things so that maybe it stays below the toxic dose? I mean, it seems like toxicity is a function of how quickly you get rid of it as well as the levels that cause problems.
Right, I think so. This underscores a lot of what we're doing at the Empire Mine and elsewhere, is that really the combination of field studies, synchrotron-based methods, physical chemical characterization of these materials, and then really critically combining that with in vitro benchtop type extractions, and then even more importantly perhaps, but more complicated, the in vivo studies, and trying to correlate all those characteristics together are really what are important and part of the interdisciplinary effort that's part of the Empire Mine study that we're doing. So I would say that to be determined.
If I could add a little bit to that. Arsenic in urine, it's known that in the human body, we methylate and then excrete arsenic for detox. And it's usually urine that's used to record recent arsenic exposure. Like I showed with the tortoise shell, keratin, which is in our hair and our fingernails, records a longer-term record of arsenic exposure. In fact, I just learned about a paper where they looked at arsenic in a Chilean mummy from the Atacama Desert. This is the region where there's very high arsenic concentration in groundwater, to show that even back then they were being affected. I don't know the answer to your question about elimination rates. Just don't work in that area, but certainly there is a rate. And also dissolved arsenic would probably be, elimination rate would be a function of the pathway. So as Chris mentioned, these particles that are able to get down into the lung, they can actually stay there for quite a while. Again, I don't know all the exact numbers for you, but I believe even years. Isn't Jeff Plumley report that in his treatise on geochemistry paper? So a real big difference, a particle that might be predicted to be low solubility, but if it sits around in the smallest part of your lung for a long, long time, maybe it will be releasing arsenic.
Okay, well, let's thank our speakers one more time and for a job well done. Thank you.
Thank you.
Thanks. This one's mine.
All right, as long as you got it. Hey, man.
Good job.